The Voyager missions have fundamentally transformed our understanding of the outer reaches of our solar system and beyond. When Voyager 1 and Voyager 2 were launched, their primary goals were to perform flybys of Jupiter and Saturn. Then Voyager 2 was to proceed to Uranus and Neptune. Little did anyone know that these spacecraft would become the most distant human-made objects in space, continuing to provide valuable data for decades. Voyager 1 and 2 were equipped with a variety of scientific instruments designed to study the planets and their moons in detail. These instruments included imaging systems, magnetometers, plasma detectors, and cosmic ray detectors, among others. The data collected from these instruments have not only enriched our knowledge of the giant planets, but also led to surprising discoveries about their complex systems and the space environment surrounding them. One of the most significant findings from Voyager 1 was its observations of the magnetospheres of Jupiter and Saturn. By studying these magnetic fields, scientists have been able to better understand the internal structures and dynamics of these massive planets. For instance, Voyager 1's measurements of Jupiter's magnetic field revealed its intense radiation belts and the fact that Jupiter's magnetosphere extends far beyond the orbit of its moon Io, which experiences significant volcanic activity due to its interaction with Jupiter's magnetic field. Voyager 2's encounter with Uranus was particularly groundbreaking because it provided the first close-up images of this ice giant. Before Voyager 2's flyby, little was known about Uranus aside from its discovery and a few basic characteristics. The spacecraft's data revealed that Uranus has a unique magnetic field tilted at an unusual angle compared to most other planets. Voyager 2 also detected that Uranus's magnetic field is asymmetrical, which was surprising and led to new questions about the planet's internal structure. When Voyager 2 flew by Neptune, it provided the first detailed observations of this distant planet, showing its dynamic atmosphere with strong winds and large storm systems. The spacecraft's close approach revealed Neptune's striking blue color, caused by the presence of methane in its atmosphere. Additionally, Voyager 2 discovered the planet's Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot, and observed Neptune's magnetic field, which was found to be tilted and offset from the planet's rotational axis. One of the most intriguing discoveries came from Voyager 1's exploration of the heliosphere's outer boundary. The data collected by Voyager 1 as it approached and crossed the heliopause, a boundary where the solar wind slows down and merges with the interstellar medium, provided new insights into the interaction between the solar wind and the interstellar medium. This data is crucial for understanding the shape and structure of the heliosphere, a protective bubble that shields our solar system from high-energy cosmic rays. The Voyager missions have also contributed to our understanding of the Kuiper Belt, a region beyond Neptune populated by small icy bodies. While the spacecraft were not specifically designed to study the Kuiper Belt, their journey has provided valuable context for future missions aimed at exploring this distant region. The success of Voyager's extended mission has paved the way for newer missions, such as NASA's New Horizons, which conducted a flyby of Pluto and is now studying objects in the Kuiper Belt. The longevity of the Voyager missions is a testament to the engineering and design excellence of the spacecraft. Despite facing extreme conditions such as intense radiation, extreme temperatures, and the vast distances of space, the spacecraft have continued to function well beyond their expected lifetimes. This remarkable durability is a result of the careful planning and robust engineering that went into building the Voyager probes, ensuring they could withstand the harsh environment of space. As the Voyager spacecraft continue their journey into interstellar space, they carry with them the Golden Records, a message intended for any potential extraterrestrial life. These records contain sounds and images that represent the diversity of life and culture on Earth, offering a glimpse into human civilization to any beings who might encounter them. This interstellar message serves as a symbolic gesture of human curiosity and the desire to reach out to the cosmos. The Voyager missions have not only expanded our knowledge of the outer planets and the boundaries of our solar system, but have also inspired a generation of scientists, engineers, and space enthusiasts. Their success has demonstrated the value of long-term space exploration and has shown that even after decades of operation, space missions can continue to provide groundbreaking discoveries. The legacy of Voyager is one of exploration, discovery, and the unending quest to understand the universe, making it one of the most significant achievements in the history of space exploration. With each new discovery, The Voyager probes remind us of the vastness of our universe and the boundless potential for future exploration. Their continued journey through interstellar space represents humanity's unyielding spirit of discovery and our enduring quest to uncover the mysteries of the cosmos. The launch of NASA's Voyager probes marked the beginning of an extraordinary journey into outer space. It demonstrated that we could observe not just Earth but also everything in our solar system and beyond. Even after 46 years, these remarkable spacecraft continue to provide scientists with new and breathtaking information about space. Although their memory is 3 million times smaller than that of our smartphones and they are 38,000 times slower than our fastest 5G internet connection, these incredible probes still lead the way in exploring space. Now, Voyager 1 has made an impossible discovery in interstellar space, one that challenges everything we thought we knew about the universe. It found something so unusual that scientists are left scratching their heads. What exactly did it find, and how does it redefine our understanding of the cosmos? Let's explore this on a special day, September 5, 1977, when something amazing happened at Cape Canaveral in Florida. Voyager 1 began its journey into space, launched by a powerful rocket called Titan Centaur. Just 15 days later, on August 20, 1977, Voyager 2 joined in, starting its adventure into the universe. Their main mission was to investigate the giant gas planets in our solar system, such as Jupiter and Saturn, and their moons. However, these space travelers went above and beyond, venturing far out into our cosmic neighborhood, breaking numerous records on their astonishingly long trip. They have traveled farther from Earth than any other spacecraft and even entered a region called interstellar space, which is like exploring a whole new part of our galaxy that no one had ventured into before. Now, Voyager 1 and Voyager 2 are more than 12 billion miles away from us, still surprising scientists with their discoveries. The Voyager probes have achieved amazing feats over the years. More than 40 years ago, they observed the moons of Jupiter and Saturn, revealing that these moons were teeming with activity, contrary to the earlier belief that they were dull and cratered like Earth's moon. Voyager 2 was the first to fly by Uranus in 1986 and, just 3 years later, it zoomed past Neptune. It remains the only spacecraft to have done so. As these spacecraft continued their incredible journey, NASA employed various techniques to ensure their continued operation. They turned off unnecessary parts and heaters to conserve power, aiming to keep the spacecraft functional until at least 2030. For the scientists and engineers who have been part of this adventure from the beginning, it's a mix of happy and sad emotions. They worked hard, and just when they thought the Voyager mission was nearing its end, a shocking discovery emerged from outer space. The information sent back by Voyager 1 and its twin spacecraft has become a treasure trove for scientists, sparking numerous discoveries and increasing public interest in space. These spacecraft were built with precision to capture clear images and gather data as they sped through space. Even before they reached the outer planets, their pictures were astonishing scientists. Voyager 1 began sending images of Jupiter while still far from the planet, leading NASA's Jet Propulsion Laboratory to eagerly anticipate the first images of Jupiter's swirling clouds and the famous Great Red Spot. But the real breakthrough came when the Voyagers discovered something extraordinary on Jupiter's moon Io. This moon, slightly larger than Earth's moon, was revealed to be the most volcanically active body in our solar system. Voyager 1's instruments detected unusual signals from Io, and the images showed massive volcanic eruptions, with one volcano, named Pele, erupting more than Mount Everest and covering an area nearly as large as France. The Voyagers took over 33,000 pictures of Jupiter and its moons, showcasing Jupiter's splendor and the diverse landscapes of its moons. Beyond this recent and more shocking discovery, the twin spacecraft had been making remarkable findings since the start of their journey. One significant surprise was the discovery of rings around Jupiter, though they are not very bright. This finding added another layer of interest to Jupiter. Voyager 2 also discovered that Europa, one of Jupiter's 53 moons, has a thick icy shell over 60 miles thick. These discoveries prompted scientists to reconsider what they knew about these distant objects and sparked curiosity about whether icy moons like Europa could potentially harbor life. As the Voyagers left Jupiter, they received a gravity boost from the planet that helped propel them toward Saturn. This boost was crucial as it allowed them to break free from the sun's gravitational pull and continue their journey into space. Voyager 1 and Voyager 2 then traveled in different directions, with Voyager 1 approaching Saturn's moon Titan, which has a thick, hazy atmosphere. Scientists were intrigued by Titan's mysteries, and Voyager 1's study of its complex chemistry provided valuable insights. Voyager 1 then began its journey beyond our solar system. Voyager 2 also had remarkable adventures. In 1986, it flew by Uranus, discovering 10 new moons, and 3 years later, it reached Neptune, providing new and detailed information about this distant ice giant. Voyager 2 even measured winds on Neptune, traveling at up to 1,000 miles per hour, the fastest winds recorded on any planet in our solar system. When the spacecraft came close to Neptune, just 2,980 miles away, it revealed Triton, Neptune's largest moon, to be one of the coldest places in our solar system, with temperatures dropping to a frigid -391 degrees Fahrenheit. Triton also featured intriguing ice volcanoes that expelled nitrogen gas and icy material into its thin atmosphere. These discoveries underscored the diversity and interest of our solar system's planets and moons, even the most distant ones. One person who made a significant contribution to this mission was the famous astronomer Carl Sagan. He was part of a team that took pictures for the Voyager mission and wanted to capture one final set of images before shutting down the cameras. These images were meant to serve as a special gift for everyone on Earth, a final view of our home from far out in space. Sagan's efforts paid off on Valentine's Day in 1990, when Voyager 1 turned its camera back toward the inner solar system and took 60 pictures. The most famous of these is called the Pale Blue, taken from 3.8 billion miles away, making it the farthest photograph ever taken of Earth. In the image, Earth appears as a tiny, pale blue dot in the vastness of space. Even after 40 years, these spacecraft continue to send us important information from the farthest reaches of space. Interestingly, the Voyager probes use an old 8-track tape system for data storage. 8-track tapes, once popular in the 1970s, were chosen for their reliability and durability. Despite advancements in digital storage, these tapes proved to be a perfect choice for the mission's needs. The information stored on these tapes is not just music but valuable scientific data about planets, moons, and the space between stars. The Voyager spacecraft have faced extreme conditions, including astonishing temperatures, space radiation, and the vast emptiness of space. Yet, these old explorers continue to function remarkably well. Their mission included a clever technique known as gravity assist maneuvers. This technique allowed the spacecraft to use the gravity of planets to slingshot themselves forward, saving fuel and gaining the speed needed to explore various destinations. This celestial dance with the solar system's giant planets played a crucial role in their journey. Voyager 1 and Voyager 2 utilized gravity assists to reach their far-flung destinations. For instance, Voyager 2 used boosts from Jupiter and Saturn to travel to Uranus and Neptune. These gravity assists were vital for the success of the Grand Tour mission. Thanks to these maneuvers, Voyager 1 and Voyager 2 were able to make their way through the solar system and into interstellar space. The concept of gravity assists, though simple in theory, involves complex execution. Voyager 2's Grand Tour required precise calculations and careful planning. Any errors in these boosts could have derailed the mission. The meticulous work of scientists and engineers ensured the success of these gravity assists, allowing the spacecraft to achieve their goals. The Deep Space Network, DSN, played a crucial role in this endeavor. The DSN acts like a space phone line, connecting us with our far-flung spacecraft through a network of radio antennas located in California, Spain, and Australia. The DSN is essential for maintaining communication with the Voyager probes. It captures faint signals from the spacecraft, which travel incredibly fast through space and become weak by the time they reach Earth. The DSN's large antennas pick up these signals, converting them into data that scientists can analyze. Additionally, the DSN sends commands to the spacecraft, allowing scientists and engineers to adjust the mission's plans and communicate with the probes. The DSN operates 24/7, ensuring that we stay connected with the Voyager probes as they journey into the unknown. Interstellar space is somewhat easier to reach than the farthest edges of our solar system. Picture the solar system as a balloon surrounded by a cloud of comet-like objects, held together by the sun's gravity. This cloud might extend halfway to the nearest star, and it will take the Voyager probes about 300 more years to approach its edge. Interstellar space begins where the solar wind, a stream of charged particles and magnetic fields from the sun, ends. The solar wind creates a protective bubble around the solar system known as the heliosphere. This bubble eventually encounters pressure from interstellar matter, forming a boundary called the termination shock. The boundary between our solar system and interstellar space is known as the heliopause. Estimates from the past place the heliopause as close as Jupiter, but more accurate calculations in 1993 suggested it is about 25 times the distance from Earth to the Sun. Voyager 1 reached this boundary around 20 years after these calculations, detecting a rise in plasma density. Voyager 2 reached the interstellar region in 2018 but did not observe changes in the magnetic field as expected, challenging previous theories. The solar wind was strongest when Voyager 2 arrived, prompting scientists to refine their models of how the heliosphere interacts with interstellar space. The Voyagers discovered numerous small changes near the heliopause but did not detect significant differences in magnetic fields on larger scales. Eventually, the spacecraft will exit this turbulent region and encounter the pure interstellar magnetic field. Saying goodbye to these spacecraft will be challenging, but they will continue to operate, powered by a system that converts heat from plutonium decay into electricity. Although their power is decreasing at about 4 watts per year, the spacecraft could continue exploring space for millions of years. Voyager 1 will pass near Proxima Centauri in 16,700 years, and Voyager 2 will follow about 3,600 years later. Even after they cease communication, they will carry golden records, copper discs with a shiny gold cover and aluminum wrapping, containing encoded messages and sounds from Earth.